My name is Rasmus Bro from University of Copenhagen in Denmark, and we're very happy today to welcome Louna Alsouki, who is doing a joint PhD with the University of Claude-Bernard in Lyon and St. Joseph University in Beyrouth, and the French Institute of Energy or something like that, I believe, maybe also. Her thesis, the name of the thesis, the title is Functional Data Regression with Prediction and Interpretability, Property Inference in Chemometrics with Sparse partial least squares. And today she's going to talk about some of the work she's been doing on imposing sparsity in PLS. So we look very much forward to that. So please go ahead, Louna.
So hello, everyone. Thank you, Rasmus. I'm delighted to have this opportunity to speak for you today and share some of the keywords of our work. I will just put the presentation. Can you see it? Okay.
Yes.
Okay, great. I have 30 to 40 minutes. That's it? Great.
Something like that.
Okay, great. Okay. So today I will be talking about a new method that we created. It's called Dual-sPLS partial least squares, and it is based on partial least squares regression with a Lasso shrinkage. This will be the scope of work. To give you an overview of the presentation, I will be covering the following topics. Firstly, I will discuss the motivation behind my thesis and the databases that we used for our analysis provided by IFPN. Next, I will talk about dimension reduction techniques that we employed, leading us to the development of dual-sparse partial least squares. Following that, I will go into the specifics of Dual-sPLS and then introduce a calibration validation method that we also developed. I will then talk about the package that we also implemented in R, its functionalities and how it operates. Afterward, I will showcase a demo of the package, giving you a glimpse on how it works. I will also provide comparative results, highlighting the effectiveness of Dual-sPLS and comparing it to other classical methods or PLS-related methods. And finally, I will conclude with our thoughts and some potential future perspective. Before starting the presentation, I would like to mention that we have already an article on Dual-sPLS in Chemometrics and Intelligent Laboratory Systems journal. And we also have the package that I will be talking about in this presentation in R implemented. It's called Dual.sPLS. Let's get started. In the field of chemometrics and analytical chemistry, one main task is to analyze the physicochemical property of complex oil cuts, complex mixtures. And this is essential in refining and transportation and storage of the oil cuts, etc. Now, the most commonly used macroscopic properties, which are here, can be the density or the viscosity of the oil cuts. In our study, the property that interests us will be stored in a vector with real values. However, the macroscopic properties are very pricey and resource intensive. Therefore, we can resort to rapid analysis methods like spectroscopy, which is widely used and exploits the physical properties of products using signals profile represented as functional data. And the advantage of these approaches are that it includes inexpensive running costs and rapidity, unlike the macroscopic properties. We can name here, for example, the nuclear magnetic resonance NMR, or the infrared, or the near infrared, etc. And so these are represented in a large matrix where the columns reflects the wave numbers and the lines will be the observations. However, the accuracy of these spectroscopic methods may be lower than the standardized methods. And therefore, we resort to chemometrics techniques that will allow us to create a predictive model for each property using the rapid analysis spectra that we have. In our thesis, the focal point relies on two main objectives. One, we would like to predict properties of novel mixtures having previous knowledge of reference ones. And two, we would like also to provide additional insights on the signal parts that drives the majority of the property.
Yeah.
Therefore,
this kid is gonna make me sleepy.
Sorry,
Oatmeal.
we turn that microphone off. Sorry.
okay. So, therefore, we will use, firstly, real data that were provided by IFPN to support the study. They rationalize the problematic concerned in this thesis. These real data will contain two sets of information. The first one provides the density of 208 petroleum cuts. This is the physicochemical property that we wish to predict. And the second is the near-infrared spectra of the same 208 cuts that are included in this real data. Now, near-infrared, in a few words, it measures how much near-infrared radiation a matter can absorb. And it gives insight about molecule-atom bonds that vary by length and strength. Now, before moving forward with the studies and using these real data, we did a pre-treatment on the real data and IR in order to remove spectral variation. Here we used a Savitsky-Golay filter, and we considered the first derivative of the NIR spectra. We used a range that will be represented by 1,557 columns, which are the variables, the wave numbers, and 208 rows. We also proposed during our work a data simulation approach in order to more accurately assess the performance of models. It produced sets of simulated data that mimics real data and will help us customize our problems. And here it will help us to reproduce situation without having to go through the whole experimental process. I will give you an example of a data that we called DSIM. On the one hand, it has a matrix X, which are the independent variables. They are a mixture of Gaussians, and we consider 300 spectra. They are represented with 1,000 variables. Figure 2 here represent the spectra, the 300 spectra. On the other hand, we also generated a response Y that fit the context of our problem. So first, we generated Y to be linearly dependent of matrix X and with a uncertainty epsilon. So this will allow us to assess the accuracy of prediction of the regression methods. But we also consider model interpretability in our study. We would like to have a model that will help us in localizing where is the important information in the spectrum that is the most related to the response. Therefore, we decided to construct Y linearly dependent of X, but not of all the variables of X, only the variables that you see here highlighted in red. So these variables will be responsible of the construction of Y, and the rest, we know now that they don't hold information concerning our response vector. So here, the good thing is that we know how many variables are responsible for Y and where they are located. Now, what is the main problem of our data? It is, of course, the number of variables that is much bigger than the number of observations, and therefore we need to use dimension reduction techniques. They can be either projection methods or penalized methods. Projection methods summarize original matrix X by building a new space of lower dimension. A well-known method is partial least squares, PLS, successfully applied in a lot of fields like chemometrics. The PLS is an iterative regression tool that handles highly correlated data. Its goal is to search for k orthogonal directions in the X space on which we will project the Y vector and reduce the dimension. With an optimization problem here, one, we will maximize the correlation between the new component, XW, and the response vector Y, subject to an L2 norm of the direction W equals to 1. And therefore, we are reducing the dimension from P variables to K smaller than P components, sorry. However, PLS sometimes lack of appropriate interpretability, and we will see this in the graphical results afterwards. Now, another form of dimension reduction techniques are the penalized methods. The penalized methods constrain regression coefficient by shrinking them towards 0. And one often resorts to the Lasso algorithm. And the Lasso algorithm, actually, it penalizes the ordinary least squares regression coefficients, which is the beta here. Okay, and it uses an L1 norm to do so. This will allow shrinkage, which will induce a form of sparsity and amounts to selecting the most important variables. Now, the Lasso is, however, sensitive to the data and does not always yield to interpretable coefficients. We will also see this in the results afterwards. PLS projection methods and Lasso variable selection approaches have important advantages that will allow us to reach our goals. So we would like to have accurate prediction, dimension reduction, and a good interpretability. Blends of the two have recent avatars called sparse partial least squares, where the PLS dimension reduction technique is used and combined to the variable selection technique of the Lasso. And the associated optimization problem is equation 3 here. You can see that we are still maximizing the covariance between the new component XW and the response Y like we do in the PLS. And we add to it the penalization of the direction of the type Lasso, so an L1 norm. This optimization problem is solved using different mathematical tools, and they are presented in the following articles here, 3. We will use these avatars of SPLS and compare them to Dual-sPLS. We will call each SPLS by the name of the main author. Now, all three of them find a solution that uses the soft thresholding operator from equation 4. It is based on the value of lambda here, this hyperparameter. It is this hyperparameter is compared to y if we apply the soft threshold to a vector y, a value y, and so each coefficient of vector y is compared to this hyperparameter lambda. If we have a value that is smaller than lambda, it is shrunk to 0, exactly 0, and the rest are shrunk towards 0. So we will have eventually a coefficient, a sparse coefficient with many zeros in it. This soft thresholding operator is used and mainly provides smoother results. Now, we were inspired by these methodologies to conceive a more generalized procedure that we call dual sparse partial least squares. It relies on the dual norm of a chosen penalty norm where shrinkage is applied. We start by the definition of a dual norm. So if we have a norm omega, the associated dual norm, denoted omega star, is defined as for any z in Rp, the dual norm is the maximum between ztw constraint to omega w equals 1. Now, why is this relevant? If we go back a few slides and look at the PLS optimization problem, we compare it to the dual norm definition, we notice that optimizing the PLS function amounts to finding the W vector that goes with the dual norm of the L2 norm, Euclidean norm, where Z equals XTY. And this motivated us to evaluate different kinds of norms, norms inspired by classical methods, and use penalization in these norms. Now, Dual-sPLS will use equation 6 as its optimization problem in order to provide accurate prediction, to extract pertinent knowledge, and to reduce dimension. The first norm that we used is a norm inspired by the SPLS that we presented a few slides ago. It's called the Dual-sPLS Lasso, and it is a combination of L1 and L2 norm. The second norm, Dual-sPLS GL, stands for group lasso. It combines groups of measurements. It applies the pseudo lasso to each group individually and constrain the total set. So here we can use the Dual-sPLS GL when we have a set of explanatory matrix X that are complementary and that can use to explain the same response Y. The third one that we propose is Dual-sPLS LS, which stands for least squares. It deals with cases where X is singular. It introduces the N1 matrix of P columns, squared matrix. And when lambda here is equals to 0, the solution of the ordinary least squares is recovered. Lastly, with Dual-sPLS R is Dual-sPLS reach. It deals with cases where X is singular and use a reach-like penalization. In this presentation, we will only focus on the Dual-sPLS Lasso. The details of the rest, or you can find it in the article that I mentioned earlier. Now, for the Dual-sPLS Lasso, we have the closed for solution that also uses the soft thresholding operator. where z here is xty, and we compare z to a parameter nu, which will control the amount of sparsity, the amount of shrinkage. And nu here is the product of two initial parameters, lambda and mu. When we deal with penalized methods, choosing the right number, the right value of the hyperparameter is always a challenge. Mu here guarantees the constraint omega w equals to 1 is not hard to find. But the challenge is choosing the right nu. And so we proposed a adaptive way to choose the nu for each iteration, which means for each component. For example, here, if we want to choose 80% of the variables of the coefficients to be exactly equal to 0, we use the cumulative frequency of xty, which is z actually, and then we will find which value of z will allow us to have this amount of zeros in our coefficients. And this value of z will be set to the hyperparameter nu. Now, this being said, we implemented the Dual-sPLS lasso, and before applying it, we resort to a calibration and validation splitting to do the evaluation. Now, the concept of calibration and validation is to divide the data into two similar sets. The larger set is called the calibration set, and it is used to create the model according to the regression method that we want to apply. Afterwards, the rest of the set is saved as a validation set, and we will use it to evaluate the validity of the model, especially in the prediction accuracy. Usually, the observations are divided according to X matrix or according to Y vector. In this case, we implemented an algorithm called Calibration. I will not go into the details of it now, but if you are interested, there's an article that will be out soon, I guess. And you can find the information there. But I gave an example of the splitting for the real data NIR. And you can see that the colored observations represent the calibration set. The black dots represent the validation set. And we can notice how the calibration covers the whole space of the observation according to components 1 and 2. Now, the Dual-sPLS method is readily available in R. And there's a package called Dual.sPLS. It is self-contained. It includes the 4 primary Dual-sPLS penalties, the PLS one, the Calibration calibration and validation splitting, real data NIR, weighted data simulation algorithm, and some functions for better visualization and evaluation. In the next slide, I will talk about what are the functions that are included in the package and how we're going to use them. So here are the functions. We have the first 4 functions of the Dual-sPLS with the 4 suggested norms, pseudo-norms. We also have a function of the PLS1 algorithm. Then, as we are in a regression that are iterative, we would like to know what number of components is the best for our model. So we also added in the package a cross-validation procedure that will help us in choosing the right number of components. Now, for prediction, we can use a classical predict function that we also add. For visualization, there is a function called print and plot that will allow us to look deeper into the model. For evaluation, we have d.spls.metric, which is a function that will compute errors like RMSE, MAE, and the R-squared determination coefficient. We also have the real data NIR with, of course, the density vector, the function that simulates a mixture of Gaussians that we can use to create data that are sparse. And lastly, the calibration and validation splitting method Calval-Xi. In this part of this presentation, we will go through a simple study, very simple one, applying all the function of the package in order to better understand how it works. We start by simply installing the package in R and loading it for the demo. Then I choose to use the real data NIR here to include in the study. I will store the NIR in a matrix X and the density in the response vector Y. Now the next step is splitting the data into calibration and validation with the Calval-Xi procedure. To apply the associated function, we set the calibration percentage to 80% here specified with the parameter pcal. And as mentioned before, Calval-Xi considers the pattern in the Y space. So in a few words, it splits the observation into subsets according to the Y value. And then it applies a calibration splitting while taking into consideration this subset splitting according to Y. And N cells is the number of subsets that we are going to split the observation before applying the Calval splitting. Here are a few commands in order to have this figure right here. In this figure, we have the observations of X according to variable 1 and variable 2. The red points are the calibration, the green ones are the validation. The point here is to see how the red set, which is the calibration, covers the overall space of the observation, which will allow us to say that the calibration that we chose may be a good representative of the whole set. Now we will apply the Dual-sPLS for the Lasso norm. We start by using the d.spls CV, which is a version of the classical cross-validation that will help us to choose the number of components that you would like to use. Our version of cross-validation, it splits the data into calibration and validation randomly, a repetitive number of times. So here, the parameters will be, first, we have to select the percentage of sparsity that we would like to have for the Dual-sPLS Lasso. Here we set it to 99%. Second, we set what kind of penalization we would like. 3, for the cross-validation splitting, we will set the ratio. So here we will divide into a 75% calibration. And lastly, the number of times that the splitting will be repeated. And then the sorry. The model with the components with the lowest mean error, the model with the lowest mean error will allow us to choose which number of components we would like to have. Then, after choosing the number of components with the cross-validation, we will apply the Dual-sPLS with the Lasso norm. Here, this small parameter set to true will give us these lines, and each one will tell us exactly the values of each parameter, lambda, mu, for each iteration, And also, it will tell us the number of zeros that we get in the regression coefficients. So these are the common number of zeros from the first component to the 10th. We can also have these informations by using d.spls.print. Here, if we select the number of components that we would like from the range that we set before, it can give us the number of zeros and the values of the hyperparameter lambda. With the with the function d.spls.metric, we can compute the RMSE and the MAR errors and the R squared. Here, I choose to compute the RMSE to plot the RMSE and MAE according to the number of variables. This, the number of components, sorry. This will help us evaluate the accuracy of prediction of the model that we are using. Now, since you are also interested in the interpretation, not only the accuracy of prediction, the function plot reveals the location of the selected variables, so here in dotted red, compared to the mean of the original data. Finally, the last part of this demo is to predict the new data, which is here the validation set. So we use the classical predict data. I also added the metrics of this new data just to show you that how the function works. Now, this demo was strictly for to better understand how the package works. Now we will apply the Dual-sPLS Lasso to real data and simulated data, and we will compare the results. So first, we will benchmark Dual-sPLS against the classical PLS, the SPLS avatars, and the Lasso. Then we will assess the prediction accuracy by computing the RMSE error for both calibration and validation, while increasing the number of components from 1 to 10. And to evaluate the interpretability and the localization, we will stack the regression coefficients vertically and compare them to the original data. We start by presenting the results for the simulated data. Our focus is on the impact of the number of latent variables according to the accuracy of prediction represented by the RMSE values. On the left, we have the results for calibration, and on the right, results for the validation. We can clearly see that the accuracy, so the RMSE values of all 5 PLS-related methods, improves globally as the number of latent components increases. And this is both for calibration and validation. Now, the Lasso performance, the Lasso algorithm is independent of the number of components, so it's represented by the dotted line in black here. Now, for as the number of latent increase from 6 to 10, we can see that all curves tend to plateau, and their RMSE values become closer and closer to each other. We observe in the zoomed plots that SPLS Lasso in red, SPLS from Sean in blue, and the classical PLS provide the best results, which with the lowest curves among the 5 PLS-rated methods and the Lasso. And based on this observation, we can say that maybe it's not necessarily to use more than 10 components to to analyze the localization and interpretability. So we can use components from 6 to 10. We choose to use 6 components to compare the coefficient localization. We stack 7 panels, original data in panel 1, regression coefficients of PLS in panel 2, Dual-sPLS Lasso in panel 3, the 3 sPLS avatars, and in the last panel, we have the lasso. If we look at the PLS regression coefficient in panel 2, we can see that it matches the shape of the simulated data from panel 1. However, they fail to localize the most important variables, unlike the sparse methods from the rest of the panels. Now, to quantify the sparsity induced by each method, we will use the L0 criterion here that computes the number of non-zero variables. And we found that Dual-sPLS Lasso, Louna, and the original Lasso performed the best by selecting a small number of variables ranging between 40 and 60. However, this improvement in sparsity did not necessarily translate to better interpretability. When we examine the variables affecting the response, so here the variables highlighted in red, we can show that some method, for example, Dual-sPLS from Louna, selects variables, a number of variables, in areas where we know that there is no information linked to the response vector. Now, based on that, we can say that Dual-sPLS Lasso provide a predictive quality comparable to its challenger and is the best in accurately localizing the important info. We are now able to evaluate the performance of Dual-sPLS Lasso on real data. So we use here the near-infrared data for density prediction. Similarly to the simulated data, RMSE curves in this figure for calibration and validation decreases globally when the number of components increases. Error also plateau from 6 to 10 components, indicating that additional components are not necessarily helpful. We again assess the model interpretability in this slide using 6 components. We stack this the same way of the regression coefficient. Now, the location of the most influential features of the spectra for density property is unknown, unlike the simulated data. But one may expect that the most meaningful variables are located in the active parts of the signals, which means maybe spectral bands with relatively higher intensities, maybe here and here. Now, if we look at the PLS, we can see that the ranges where we have a spectral variation are larger than the ranges compared to the original NIR data, which makes it difficult to identify the specific spectral bands associated with the density, and this may lead to ambiguity. All sPLS actually have smaller ranges, and especially sPLS from Louna and Dual-sPLS Lasso and the original Lasso show sparser results. If we look at Dual-sPLS Lasso, we can notice 2 important features. One, Dual-sPLS Lasso coefficients are smooth and contiguous, whereas sPLS, for example, from Sean and Zurich, we can see that the coefficients are more scattered across the wave number axis. Second, a second interesting feature of Dual-sPLS Lasso is the lack of response in this area here, while the rest provide a selection of variables in this area. We cannot explain this chemically, but we can say that despite this discrepancy, Dual-sPLS Lasso still performs almost as well as its competitors when we look at its accuracy of prediction. So with these results, we will move on to the conclusion. According to the work that was completed, we can say that the Dual-sPLS is a method that where the advantages of the partial least squares are not lost. We still have accuracy in prediction. We still have an easy algorithm. It is a general way that deals with complementary data and provides sparse results with good localization. Now, for the upcoming work, we have a few papers almost ready to be submitted. One is for the package manual with chunks of codes explaining how to use the Dual-sPLS package. The second concerning the calibration and validation splitting procedure, Calval-Xi. And the last one will provide explanation on the NIR data acquisition along with the data itself. And we are also interested in studying the uncertainty of the PLS estimators, as there are not very much, there are very few studies concerning this matter. I leave you with a few references here, and I thank you for your attention.